I'm going to talk today about nuclear stellar clusters and supermassive black holes. This is work done together with Abbas Asghar and Ross Church at Lund University. The first part of the talk has appeared already in BINARIES in 2021, and the second part is in preparation and will be submitted shortly. So the first thing to think about is the build-up of a nuclear stellar cluster in the centre of a galaxy. And this figure shows work done earlier by Antonini and others. And the idea here then is that stellar clusters, shown as the cluster of black dots here, spiral inwards towards the galactic centre around a pre-existing supermassive black hole denoted here as the red dot. And what we can see happening is that the stellar clusters spiral in, they're tidally disrupted, and they merge to form a nuclear stellar cluster around the supermassive black hole. So key idea number one then in this talk is a question, chicken or the egg? Which comes first, the supermassive black hole or the nuclear stellar cluster? So can we have a supermassive black hole forming after we have a nuclear stellar cluster in a different way to what we've just seen with the Antonini picture, where they had a pre-existing red dot, the supermassive black hole, and a stellar cluster form around it? Can we have a process where we make the nuclear stellar cluster first and have a supermassive black hole form and grow within it? This is not a completely abstract question. Observations show the following. M33 is a local galaxy, a satellite of Andromeda, and when one looks inside the very centre of M33, one finds a nuclear stellar cluster, but it does not contain a supermassive black hole. And it's not alone. There are other galaxies showing the same property. On the right-hand side here, we have the velocity dispersion as a function of central supermassive black hole mass for a number of galaxies. So each data point here is an individual galaxy. We can see the Milky Way denoted here with a black hole mass of a few million solar masses and a velocity dispersion of around 100 kilometers a second. But there are a group of galaxies like M33 which have much lower velocity dispersions in their nuclear stellar clusters and really quite firm upper limits of masses of supermassive black holes. So black hole masses of 1,000 or so solar masses or lower. So there's a group of objects which contain nuclear stellar clusters, a group of galaxies containing nuclear stellar clusters but no supermassive black hole, which at least suggests that we can form a nuclear stellar cluster before we form the supermassive black hole. I should explain that M33 is a very quiet galaxy. It's bulge-free, a classic bulge-free spiral galaxy, which really means that we can't have had a major merger. Because if we had a major merger, that would be a way to eject a supermassive black hole, but that would leave us with a bulge from a burst of star formation, and we do not see that in M33. So what we did in the first paper then is the following. We simulated the merger of stellar clusters. We actually model using n-body code, n-body 6, a set of stellar clusters and had them spiral together. We follow the growth of the nuclear stellar cluster, and some of the clusters have intermediate mass black holes in and some do not. Where by intermediate mass I mean masses of between a few hundred up to 1,000 solar masses as seen on the table on the right. Crucial point here is we don't begin with a supermassive black hole. So we just have the stellar clusters, which may or may not contain an intermediate mass black hole, spiral together and merge to see what we get and to see what happens to those intermediate mass black holes. So we're building up a nuclear stellar cluster then by having stellar clusters spiral inwards, and some of those stellar clusters contain an intermediate mass black hole, denoted as the black dot in this figure, and some do not. And also we include later the effects, or consider the effects of gas inflow into this nuclear stellar cluster, which as we'll see helps grow the intermediate mass black holes to supermassive black hole status. So key idea number two then is that intermediate mass black holes may form via runaway mergers in dense stellar clusters. So we're thinking about making the IMBHs within the individual stellar clusters before those stellar clusters merge to become the nuclear stellar cluster. And they can grow in a number of ways. They can grow via runaway collisions whilst the stars are still on the main sequence, so forming a very massive main sequence star which then collapses directly to make a black hole of mass scale roughly 100 solar masses perhaps. Or we can feed a black hole by, for example, collisions with other stars or the tidal disruption of stars, where then some fraction of that gas at least will then accrete into the black hole. What I show here then is calculations from Asghar et al. 2017, where they're looking at the growth of these IMBHs using a Monte Carlo code to model the n-body evolution of the cluster. And what we see here then for a set of stellar clusters of each containing 100,000 stars, the mass of the most massive black holes in them, and we see that we can get to mass scales of over 1,000 solar masses in some cases. And the solid dark line shows the median value as a function of a log of time. And so what we can see here is in something like 10 to 40% of cases, the clusters actually produce an IMBH. So crucially, not all stellar clusters will contain an IMBH, we think, but some fraction, perhaps 10, 20, 30% of them will do. So key idea number 3 then is that 1 plus 1 equals 0. So what do I mean here? Well, imagine we have a situation where we're merging clusters to form a nuclear stellar cluster, and 2 of those clusters happen to contain intermediate mass black holes. Then the question is, what happens? So our nuclear stellar cluster contains 2 intermediate black holes. The question is, what happens to those 2 black holes? Well, what happens is they form a binary. They find each other very quickly because the mass of the intermediate mass black holes are much larger than the stellar masses, but much less than the cluster masses. So actually the merger process of the clusters is unaffected by the IMBH presence, but because they're much more massive than the stars inside the cluster, they sink very quickly and they find each other. So 2 intermediate mass black holes very quickly we form a tight binary, and that's shown on the left-hand side here. This is in our published paper. And that binary can be quite eccentric, I mean very eccentric indeed, and that enhances or shortens the merger time. It enhances the gravitational radiation loss. So our 2 black holes in an IMBH will spiral together and merge as they lose angular momentum and energy via gravitational waves. But crucially, when those 2 black holes merge, they will get a recoil kick. This is a well-known property of merging black holes. It's actually because when you have the final in-spiral, it's on a timescale shorter than the single orbit, and the asymmetry of the emission of gravitational waves means that gravitational radiation, which carries away momentum, of course, is preferentially in one direction in the final in-spiral, and therefore the merged binary gets a recoil kick in the opposite direction. This is a small effect. It's a small fraction of a large number at the speed of light, but that's still an interesting speed for us here, and it's shown on the right-hand side in this figure from calculations of this recoil kick, which show recoil kicks of many hundreds of kilometers a second. The recoil kick received by the merged binary is a function of the mass ratio of the 2 black holes. So if we have a sufficiently low mass ratio, in other words, one black hole that's much less massive than the other one, the recoil kick can be sufficiently low that the merged binary is retained in our nuclear stellar cluster. Otherwise, it's ejected from the nuclear stellar cluster. So key idea number 4 then is 1 plus small is larger. So if we have a black hole binary with a mass ratio less than around 0.15, the black hole binary can be kept inside our nuclear stellar cluster and then can continue to grow. So we're thinking that in some cases, if we have 2 IMBHs in the center of our nuclear stellar cluster, even though they merge, they can be retained, providing one black hole is much more massive than the other, and then that black hole can grow either by tidal shredding of stars, collisions with stars, or just gas infall into the nuclear stellar cluster region, some of which then accretes into the black hole. So what we have here then, this is the second paper that's about to be submitted, is we've actually calculated then properties of a population of nuclear stellar clusters. So we built nuclear stellar clusters from lower mass stellar clusters, drawing them from a sensible population, randomly giving some of those nuclear stellar clusters intermediate mass black holes and having them merge. And what we show here then is a function of log of nuclear stellar cluster mass is we have the log of the black hole mass, the massive black hole mass, from the initial merger process. And in some of these clusters that we've made, the nuclear stellar clusters are made from basically a number of stellar clusters, and then there's different situations. So the blue dots at the bottom, none of the stellar clusters coming in had an intermediate mass black hole, randomly by chance, and so we see that there's a population of those. And for low nuclear stellar cluster masses below about 10 to the 6 solar masses, it's very common for the nuclear stellar cluster form to not have an IMBH, just because we've made it from a sufficiently low number of stellar clusters. The ones containing one intermediate mass black hole are shown as an orange colour, and those containing many seeds are basically shown as the sort of cyan pinky colour with 2, and with larger than 2, so 3 or more IMBHs, are the yellow dots. And we can see then as increasing nuclear stellar cluster mass contain on average more IMBH seeds, simply because they've been built from more stellar clusters. That's not surprising. So what we can see here then is that a population of nuclear stellar clusters sometimes contain IMBHs and sometimes not. And remember, what we're trying to explain ultimately is objects like M33, which is shown on the left-hand side here, with a nuclear stellar cluster mass a little about 6.3 in the log scale, doesn't have an IMBH, whereas the Milky Way, with a nuclear stellar cluster mass a little over around 10 to the 7.3 or so, does contain a massive black hole today, of course. So the key idea here then is that the Milky Way is a nuclear stellar cluster with an IMBH which grew via gas accretion to make the supermassive black hole we see today. So if we allow ourselves for the black hole to grow at 10% in Eddington rate over 4 gigayears, so this is a time when we know from quasar observations that galaxies are most active, that the black holes are growing on average. So we give ourselves 4 gigayears and say we're at 10% Eddington over that time, then we grow the black holes to what we see in this plot here. So now we see that the black hole masses have grown considerably from what we saw before. We've allowed also for the binaries, if there were 2 IMBHs, to merge, and we only retain them if the massive black hole is much more massive than the lower mass one, that mass ratio less than 0.15 as we saw earlier, so we have a low kick speed. And what we see is that Milky Way and M31 are easily matched this way. We can easily grow black holes to mass scales of 10 to the 6, 10 to the 7 solar masses, as observed in the centre of many galaxies when we have nuclear stellar cluster masses around 10 to the 7 or so. The key idea with M33 then is that we have a nuclear stellar cluster either without an IMBH or we have no gas inflow, so the black holes don't grow to supermassive black hole sizes. So in other words, we can easily explain that M33 does not contain a supermassive black hole simply because galaxies with nuclear stellar cluster masses as low as M33s quite often simply never have an IMBH in at all, because again they've been formed from a relatively small number of stellar clusters. So in general then we can look at the actual binary black hole, occupation fraction, the fraction of nuclei that contain a supermassive black hole. And we show that in the plot here on the left and the right, where we plotted versus stellar mass of the galaxy and nuclear stellar cluster mass on the right hand side. And what we see is matching observations rather well, namely that for low galaxy masses or nuclear stellar cluster masses down at around 10 to the 6 or so, the fraction of those that contain a supermassive black hole is rather low. So M33 is not surprising, and our modelling can match M33. Whereas when we get up to mass scales comparable to the mass of our own galaxy, or M31, the occupation fraction is much higher and indeed matches observations. So let me quickly summarise then. We've shown chicken or egg. We've talked about supermassive black holes forming after nuclear stellar clusters. This makes sense given the observation of M33 that has a nuclear stellar cluster but no SMBH. We had the idea that the nuclear stellar clusters form from stellar clusters spiralling and emerging, and some of those stellar clusters may contain intermediate mass black holes. We saw the idea that if we had 2 of those intermediate mass black holes, if they merged in the nuclear stellar cluster, they may get ejected, so 1 plus 1 gives us 0 IMBHs, but providing the mass ratio was sufficiently large, or small rather, that the more massive black hole was much more massive than the less massive one, mass ratios less than 0.15, then we could actually merge them and retain them and grow subsequently. So Milky Way is a nuclear stellar cluster containing at least 1 IMBH that's grown by gas accretion, whereas M33 had a nuclear stellar cluster without any IMBHs, or at least no gas accretion subsequently. Thank you.